regarding your muddy points, so a bunch of none as such and nil. One question about the still unsure as to if yk represents a linear quantity or a non-linear one. So how should I answer that, anybody? So this confusion, you are getting to the right part, but this confusion about what is linear is has to be addressed. So we are dealing with an OD, so we are trying to solve this OD, du dy dt, I think, is equal to minus alpha y is the one that we looked at, and so this is obviously a linear OD because my y as well as its derivatives appear without any product terms. Then when we did a discretization of this, we still have this form where again there are no product terms. So the OD or the FD is linear in the sense that there are no product terms. So what we mean by linearity in this context should be very clear from all of your studies. What do we mean by linearity of OD or FD? Solutions must satisfy superposition principle. Superposition principle applies to solutions. So if I have some zk is equal to yk1, say w1 plus w2 yk2, then this zk is also guaranteed to be a solution of my original FD. Does that make the yk linear? What is the meaning of a linear solution? Linear solution to me would imply that y as a function of k should go linearly. That's what we typically mean by a linear solution or linear function. That's not the case at all, right? We have got an exponential decay. So it's the question itself is flawed in that yk, we cannot judge its linearity or non-linearity. That's not a question even, because we are talking about the governing equation being linear. So that solutions, be they linear or non-linear, if they are satisfying the original solution by original equation by themselves, then linear combinations of them will also satisfy. That's all that we are implying by linearity, okay? Nothing else. It should be clear to you all. So that's how I would answer that question. I hope that satisfies whoever asked that question. By the error in the solution, so solutions, we saw that that little exercise that we did, we saw that when we plotted the error as a function of k, so the error grew and then decayed, right? So that was as argued because my solution itself is decaying. So it's a exponential solution, exponentially decaying solution. So here, if there are errors, the actual magnitude is also large, so the errors will be magnified somewhat, and that will continue because the errors are of course increasing as we go along. Errors are getting compounded, but the actual is because the value itself is decreasing to 0, so error of 0 will also be close to 0. So that way the error is also decreasing. So this was what we found for the forward Euler and the backward Euler. The Crank-Nicolson in this graph was essentially 0. So I hope you can go back and zoom into the axis and see what the Crank-Nicolson is doing to get a feel for that. But this is not our main interest in this course. In this course, we will not be having situations where we will solve these FDs using their analytical solution. If that was possible, then it would not be a computational error acoustics exercise. So what we are interested in is developing numerical schemes that can solve these kinds of equations. So as we discussed, the discretization of space and time is fundamental to all computations, and the particular equation that we will be computing is the linearized Euler equations. So we will lead up to this. So assumptions in the Euler equation should be clear, linearized, is that it's inviscid, there is no thermal diffusion also, so it's no non-conductive, and it's linearized, but the base flow is not necessarily homogeneous. Then we saw that the interest in this is because if we have a homogeneous base flow, then we have a very clear notion of what is acoustics. So this is relevant for acoustics, but this is a like a superset of acoustic flow, acoustic problems. So we will develop schemes for solving this. One thing to be noted is, so when we can write this quickly, don't quote me on these right now, but it will be something like, or so it was things like this, and then just write the next equation, the momentum equation. Maybe there will be a few more terms. So there will be the rho prime u0 dot grad u0 and the rho naught u prime dot grad u0 is equal to f. So again, the particular details you will recall from your previous discussion, but the main point that I'm trying to make here is that there are only first order spatial derivatives occurring here. So when we look to understand the behavior of our numerical schemes for spatial discretization, we will be interested in only the first order derivative. We will not inquire about the higher order derivatives, even though you might think that, oh, we are looking at the wave equation, which is a second order equation. So why are we not interested in the second order derivatives of space? It turns out that we will solve the linearized Euler equation, which is a coupled set of first order equations. So if you were to do some clever trick, you will end up with a second order equation that we know, but we will not be solving it in that fashion. We will be looking at it as a set of coupled first order in space finite difference equation. And so the interest is in looking at, in general, terms like del u, del x and del u, del. So we'll be interested in this kind of thing, where u now is not the velocity but any variable, including density, pressure, velocity, temperature, whatever variable you might be interested in. So u is just a variable in TAMS notation. So we'll be first looking at discretizing this in space, and next look at del u del t. So this is spatial discretization. So you might be familiar with various ways of or various overarching ways of solving or posing numerical schemes. There are mesh based methods, but there are also what are called mesh free methods. If you are interested in the latter, please take Professor Prabhu Ramchandra's course. He talks about mesh free methods. I am not going to talk about that. In CA, the interest has always been in mesh based methods, in the sense that we have a domain which we are discretizing using some possibly complicated mesh depending on the domain. Can have all sorts of crazy mesh and so on, but there is a mesh on which we are looking to solve the governing equation. There might be a body here, so maybe this part of the geometry is a body, solid body. For example, it's a like a forward facing step. So there is flow, there is a step here, it's like this step here. So there is flow coming and there is a step, and so it has to go over that, and we might be interested in solving that. So then this will be not part of the mesh, but whatever it is, we will be thinking that there is a mesh, a spatial mesh over which we are interested in the flow solution, and we'll of course assume that the mesh is not moving. Okay, so let's keep things simple. So our numerical schemes are developed for 1D problems, 1D scenario. And then we just extend them to 2D or 3D as the need arises. Okay, and that extension is not problematic ever. In particular, because we are looking at first order schemes, first order derivative, so there is no cross coupling, there is no interest in say del u or del 2u, del x, del y, things like that. Okay. So we will only have del u del x or del u del y or del u del z to worry about at any given instant in terms of discretizing them. So there is no particular challenge in extending 1D case to 2D or 3D. So given that we are now thinking of a 1D problem, so the simplest 1D mesh is the uniform one. So this is the domain. Domain has a start or a left end and a right end, and it will have uniform grid because we are simple. So we'll number the, so this is the x direction because it's a 1D problem. So the Cartesian x direction is a natural quantity to look at, and this is x equal to 0. This is some x equal to L. Your spacing is a constant delta x because again we have got a uniform mesh. And we are looking to discretize this derivative on this uniform mesh. So we will number these mesh points as is usual, as 0, 1, 2 and 2, maybe n, or maybe I'll keep yeah, small is fine. And we are interested in evaluating the derivative at this point. Now as we go on, you will notice, you will appreciate that we have got the solution is, solution is u is known on the mesh, that is it is known at these discrete points, and what we want is del u del x on mesh. So we want the del u del x also on the mesh, so that then next later on we will then evaluate the del u del t using that knowledge of del u del x, so that we can time integrate and go to the next point in time. So we will come to that as we go along. Right now we are just starting from the basis that there is a solution u known on the mesh, and we want to find out del u del x also on the mesh. This is a standard situation for posing a numerical method for a derivative operator. So in this context, let us say that this is the Lth mesh point, and we are interested in finding the derivative at the Lth mesh point. So one very common way is to have a finite stencil. That means that when I am interested in finding out the solution at the Lth grid point, I am going to say 2 points to the left and 2 points to the right. I am going to use the information of the solution u at these 5 points and somehow massage those or mix them together and then come up with some idea of what is del u del x at that point L. So what we are saying is that del u del x at x equal to L delta x is some function of u at L minus 2, u at L minus 1, u at L, u at L plus 1 and u at L plus 2, where the subscript denote the grid points. Okay. So u at L is the solution at the Lth grid point. So we want to find a function that can approximate the derivative at u for a general u. We do not know, we didn't have to derive a scheme that is agnostic or doesn't care about the real solution. So irrespective of whatever solution you have, you should have a good approach for approximating the derivative of that function at the particular grid point. Now if you have got more computation at hand, then you will extend this. You will have a larger stencil, that is, you will take maybe one more point on either side. Take one more point on either side, so this will become a 7-point stencil. And so you will have to now add up u l minus 3 and u l plus 3 also to the mix and see what additional benefit that gives you or not. It's not needed. In fact, if you want to now be more adventurous, then you are out of grid points at the other end because your domain is never this short. But suppose your domain is, you are reaching towards the end of this boundary, the right end, then now you are out of points here, but you still want to improve your estimate. So then you might want to use these 6 points. That is all the points on the grid, because this example is so coarse. All the points on the grid, and still want to estimate this, then you should have ul minus 4, but no ul plus 4, because that's not there in your domain, which is fine. We might still want to have a better estimate of the derivative for that.
So considering we're dealing with waves propagating in a certain direction, my guess is that we suppose like we're the wave is traveling from 0 to L. So when we calculate our scheme, do we bias the points ahead, say like UL 3 UL minus 2 minus UL minus 1 plus UL by delta?
So that would be similar to what is an upwind scheme in
Yes,
in CFD. So that is relevant for convection dominated problem, but not for wave dominated problems, because again you do not know where the wave is going to come from, and your scheme cannot be so intelligent, because then you are spending too much time on developing the perfect scheme for this particular problem. Then that's not very general. So we want to develop schemes that are more general. In that sense, we do not know which way the wave is coming from. For example, you might have a source here which is generating a wave which might be traveling back and forth.
Right.
So then how do you account for that? Are you going to change the numerical scheme all the time? You can do that. That's an upwind scheme, but that is not useful, or that's not found to be of any use in acoustic problems. Solution U is known now. For example, it might be the initial condition. You have to tell me the initial condition. So I'll start from there. I'll evaluate del U del X, and then using the fact that suppose U is rho. So then I'll have del rho prime del T is equal to minus U0 dot del rho prime del X if it's a 1D problem, minus other terms. So rho naught del U prime del X and so on. So here you have density, you have got velocity, you find out the derivatives of them, you form the right hand side, then with that you evaluate the left hand side, then you integrate this. That's our program. So right now we are saying that we know what the solution is at the current instant on the entire mesh, maybe from the initial condition, maybe from a later part in our solution process, and we just wanted to go to the next step. As part of going to the next step, it's a two-step procedure. We first have to evaluate the derivative, the spatial derivative, and then we will equate that to the time derivative, and then integrate the time derivative. So it's a inverse approach. Okay, so we'll see how that affects our numerical schemes also. That we first differentiate in space, but then we integrate in time to go to the next step, and that must be informing our numerical schemes. So in this context, you all would have heard of Taylor, truncated Taylor series approaches. So one way of stating the essence of this is that if we have got what is a consistent scheme, that is, if we were to grid up our domain with a finer mesh, our solution should improve. Okay. And so this tailored approach to defining or deriving the numerical schemes gives us that benefit, that gives us a consistency in our approach. Okay. So this is how it goes. What we again said is that, so we'll now specialize, and as part of your ungraded homework, the next one, you will see that I'm also asking you to look at the more general case. So we'll now specialize to central difference scheme. What that means is that whenever we are interested in the derivative at the lth grid point, we are going to take an equal number of grid points to either side of it. If we are towards a boundary, if we are close to a boundary, in which case this point is not there because there is only one more point left after the grid point, then this central difference will not be relevant, and so you have to have forward or backward differences, which you will again work out as part of your homework. But right now we are just starting off, so let's fix with central difference. So then this is the L minus 1th, L minus 2th grid point, L plus 2th, L plus 1th grid point, L plus 2th grid point, and we have got the solution known at all these grid points. So this is a solution, this is a solution, something like that. Maybe that's a solution. So this we'll call as UL. This is UL plus 1, UL plus 2. So these are all known. So we want to write our scheme as del U del X at L is, and to make things simpler, we'll pose a linear combination, a linear mixing of these things in the sense of A0 UL plus A1 UL plus 1 plus A2 UL plus 2 plus A minus 1 UL minus 1 plus A minus 2 UL minus 2.
Just hit me. Why are we considering 5 points for central difference rather than just a standard 3?
So we'll deal with it. This is just a number. So we'll generalize it for n-point stencils.
Okay.
So this is just an example, but you can have a 3-point also. We'll come up. I'll probably do that as a class exercise, and then I'll have you do a look at it for the 5-point stencil or 7-point stencil, which is favored by TAM. Okay. So for your graded homework, you are going to do a 7-point stencil that is shown by time to be adequate for most purposes. You can use, depending upon your computational resources, you can go up very high. So 15-point schemes have also been used, depending on how much of accuracy you want. Yes, so there are other issues related to that. So it's a balancing act. So it's a pros and cons that you have to do. Okay, so this is the overall setup of our scheme.